In today's lesson, we will be determining concavity of functions. So get ready. There's a lot to write down, so you might want to write small on your notes. And just make sure you're taking it all in and trying to visualize all these graphs as we are changing from functions, derivative graphs, and second derivative graphs. Okay, so let's start with an f of x concave up graph. So I'm just going to sketch a concave up graph. So I want you to think about the derivative graph. So derivative graph is describing the slope of f of x. So it is decreasing, it's 0, and it's increasing. So it's negative, 0, positive. So the derivative graph, so it's decreasing, so it's negative. And then the minimum point, it's 0, and then now it is positive. So notice when f of x is concave up, f prime of x is increasing. So now let's consider the second derivative. So the second derivative is describing the slope of the derivative. So if it's increasing, it is positive. So that second derivative would always be above the x-axis. So f double prime would be greater than 0. So what we'll be doing today is, if we have this, if the second derivative is greater than 0, that concludes that the original f of x is concave up. So you can probably guess what's going to happen when we do concave down, but I'm still going to go through that process. So concave down. So this is f of x. So f prime of x, that's describing the slope of f of x. So it's increasing, it's 0, and then it's decreasing. So f prime of x, if it's increasing, so it starts out positive, then it has to hit 0, and then has to go negative. So as you can see, when f of x is concave down, f prime of x is decreasing. So then the second derivative is describing the slope of the derivative, and so it's decreasing, so it would always be underneath that x-axis. So, that's supposed to be double prime. So f double prime is less than 0. So same thing, if the second derivative is less than 0, we can conclude that the original function is concave down. Okay, so here we have an example. F of t equals t to the third minus 12t squared plus 45t plus 7. And our goal is to find the intervals of concavity. So to know about concavity, we want to look at the second derivative. So we will be making a sign chart, but of the second derivative. Okay, so f prime of t is 3t squared minus 24t plus 45. And then the second derivative is 6t minus 24. And we want to set this equal to 0. So add 24, divide by 6, we'll have this critical point at 4. Okay, so for the sign chart, so the intervals, negative infinity to 4, 4, and 4 to infinity. Okay, so we're looking at second derivative. If we plug in negative infinity, it'll be negative here, 0 here, positive here. Okay, so when the second derivative is negative, we are making a statement about the original function. It is concave down, and it is concave up when it is positive. So remember, we're using derivatives to make conclusions about the original function. So I guess that should have been f of t, but so f of t is concave down from negative infinity to 4 because f double prime is less than 0. And then f of t is concave up on the interval 4 to infinity because f double prime, oh, I keep doing x and t. Gosh, need to be careful here. F of t is greater than 0. Okay, the other part of this lesson is talking about points of inflection. So I'm going to sketch a graph. A point of inflection here, it is the point where a graph changes concavity. So let's write that down. Point where a graph changes concavity. So as you can see, it's concave up here, and then all of a sudden there's like this middle point where all of a sudden it's changing. Okay, now it's concave down. So now I want you to think of this as an f of x function, and we're going to sketch the first derivative and second derivative graphs. So first derivative is telling you the sign of the original function. So it's decreasing, it's 0, it's increasing, it's 0, it's decreasing. So on the derivative graph, so there's these zeros here and here, and then so this whole part where it's increasing on the derivative graph, it would go up and down, and then negative, negative on the ends. So the point of inflection on f of x would be that maximum point on f prime of x. So now let's convert that into the second derivative. Okay, second derivative describes the slope of the first derivative. So positive, 0, negative. So where it's 0, that's where it's crossing the x-axis. It's positive, 0, negative. Okay, so now the point of inflection. Point of inflection here on f of x is a maximum point on f prime of x. It's a 0 on the second derivative, where the second derivative is changing from a positive to a negative. So a point of inflection, the point where a graph changes concavity, is where the second derivative changes signs. So for the next example, if I have f of x equals negative x to the third plus x squared minus 4, and our goal is to find the points of inflection. And what we just said is that a point of inflection occurs when the second derivative changes signs. Okay, so let's take the first derivative, which is negative 3x squared plus 2x. Let's take the second derivative, which is negative 6x plus 2. Let's set this equal to 0 so that we get x equals, subtract 2, divide by negative 6, we'll get a positive 1/3. So that's a critical point on the derivative. So this is the point where it's going to change signs, but I want to do a sign table just to give us a visual. So intervals negative infinity to 1/3. And 1/3 to infinity. Okay, so, and we're looking at signs of second derivative. So we'll be plugging in things here. So if we plug in negative infinity, negative times a negative is a positive. Here it's 0. and then this will be negative. So as you can see, this is the point where the second derivative changes signs. And this is giving us information about f of x. So what you would say is f of x has a point of inflection at x equals 1/3 because the second derivative changes sign. Okay, so we are going to just sketch a graph, and this will be a second derivative graph. Okay, so I just kind of picked some points, and I'm going to go up and down. This will be a sharp point, this will be a curve. Okay, so just kind of a general sketch. This is a second derivative, and our goal is to use this graph to describe the points of inflection on f of x. So a point of inflection occurs when the second derivative changes sign. Changes signs. Okay, so this is a second derivative. So here it's positive. Here it's negative. Bam, that's a point of inflection. Here it's going back to positive, point of inflection. Here it's going back to negative, point of inflection. So our statement is about f of x. So f of x changes, remember what point of inflection is. It changes concavity. So that is a point of inflection at x equals, that's -4, at x equals 0, and at x equals 6. Okay, similar idea, but instead this will be a graph of the first derivative, not the second derivative. Okay, so I'm going to sketch a graph. Okay, so finding points of inflection is when the second derivative changes signs. So I have, let's see, this is first derivative, so it is increasing, decreasing, increasing, decreasing, increasing. So this is basically would be like the second derivative describing the slope of the derivative. So it changes signs at min and max values at these extrema. And our statement is always about f of x. So f of x changes concavity or has points of inflection at, let's see, at this x, this one, and I didn't put that one at a very clear one, let's say here. So that would be at x equals -4, x equals -1, x equals 2, and x equals 7. So there is your full lesson on determining concavity of functions. It can be confusing looking at all the different forms of graphs and knowing what each one represents. But there you have it. So good luck with your lesson.